Amid the Sierra Nevada mountains of California, the Orville Dam was built as a colossal barrier to restrain and control a body of water exceeding 5 billion gallons. It is the tallest dam in the United States, a massive structure of concrete and rock designed not only to store water, but to contain floods powerful enough to devastate the entire downstream region within minutes. Yet, holding back water at this scale has never been simple. Complex mountain geology, extreme hydraulic pressure, and the engineering limits of the era turned Orville into a challenge many believed was too risky to realize. So, how was this dam built to stand against such immense force? Orville Dam, located in the city of Orville in Northern California and completed in 1968, is the tallest earth-filled dam in the United States and serves as the water lung of the entire California State Water Project. Its reservoir holds more than 1 trillion gallons of water, helping regulate river flow during the spring snow melt, prevent flooding in the rainy season, and maintain a stable water supply for California during the dry months. However, in early 2017, as record-breaking rainfall poured into the watershed, the dam's main spillway failed. Concrete slabs only 20 to 25 centimeters thick were torn apart. Water seeped underneath and generated intense uplift pressure, and the weakened bedrock eroded into a massive crater. Immediately after the crisis, the state launched a large-scale reconstruction project. Repairs began in May 2017. The first phase was completed by the end of that year in time for the next rainy season, and the entire spillway system, both the main and emergency structures, was fully rebuilt by the end of 2018. The first items that had to be repaired were all the fractured concrete sections and the weakened foundation left behind after the incident. The construction crew had to remove more than 1,000 meters of the spillway, tens of thousands of tons of concrete using excavators, hydraulic breakers, and controlled drilling and blasting. This phase alone took several weeks because the spillway's 35 to 40 slope made it extremely difficult for heavy machinery to operate and move safely. During the demolition process, as hydraulic breakers shattered the old concrete layer, workers constantly sprayed water over the area to keep fine dust from spreading into the air. The water also helped cool the breaker tips and reduce the chance of concrete fragments flying off dangerously. This made the removal work safer and more controlled, especially on the steep surface of the spillway. Some concrete sections weren't visibly damaged, but the internal steel reinforcement made them nearly impossible for excavators and hydraulic breakers to penetrate. To deal with these stubborn areas, the crew drilled hundreds of small holes in a dense grid pattern, then placed low-charge explosives and detonators into each one. All the wiring was connected by hand and carefully inspected to ensure the blast would trigger safely and uniformly. When activated, the controlled explosions fractured the concrete along the intended lines, allowing workers to peel away the remaining sections without harming the bedrock underneath. Thanks to this method, the entire surface of the old spillway was successfully cleared. Once each concrete slab was broken free, it was loaded onto heavy-duty trucks and hauled out of the work zone in batches. As the old concrete blocks were hauled off the spillway, they weren't discarded. Instead, they were moved directly to an on-site recycling zone. Dump trucks released each load into a feed hopper where a high-capacity crusher broke the slabs into smaller pieces. The material then passed through a vibrating screening system that sorted it by size, from large aggregate down to finer particles. Any material that met the required specifications was carried along long conveyor belts and stockpiled for reuse as base layers, subgrade material, or structural fill for the new spillway itself. After the old concrete was completely stripped away, engineers continued excavating into the eroded soil and rock to remove any loose material, exposing the natural bedrock underneath. The foundation required to build a stronger, more resilient spillway. After the entire site had been cleared, the next step was to build a solid cement foundation. Heavy-duty trucks began loading batches of dry cement pre-mixed with gravel and sand, forming RCC, roller compacted concrete, a material designed for massive structures that demand extremely high strength and durability. At the central mixing station, a dump truck was filled with about 21 cubic yards of RCC every 5 minutes, then immediately sent to the construction zone perched on the steep mountainside. Once on site, the truck lifted its bed and released the RCC onto the spillway surface, forming a thick layer that was spread into long continuous strips parallel to the spillway channel. Bulldozers followed right behind, leveling the mix and adjusting the slope, width, and elevation with centimeter-level precision to ensure the foundation bonded tightly to the natural terrain. Immediately afterward, high-tonnage vibrating rollers made multiple passes to compact the RCC. transforming the loose material into a dense solid concrete mass, firmly locked to the underlying bedrock. This cycle of placing, grading, and compacting was repeated continuously layer by layer until the entire new foundation reached the required thickness, hardness, and load-bearing capacity. After the RCC layer was compacted to the proper density, workers sprayed a thin film of water over the surface to keep it moist and activate the cement's hydration process. At this stage, a specialized leveling attachment mounted to the boom of an excavator began its work. The wide leveling blade was lowered onto the RCC surface and moved back and forth, shaving down high spots and filling in low areas to create a continuous plane that matched the design slope. Thanks to its hydraulic controls and precision sensors, the machine could maintain accuracy down to the millimeter. At the same time, the crew quickly pressed the rebar dowels into their marked positions, preparing for the structural concrete layer that would be placed on top. Finally, workers inspected the entire surface using laser levels to ensure the RCC base met the required elevation and flatness. Next, the construction team began installing the green epoxy-coated rebar, a specialized corrosion-resistant steel designed to withstand high-velocity water flow. Each bar was lifted into place, set on small concrete spacers to maintain the correct elevation and tied together into a uniform, square grid that covered the entire spillway surface. In areas near the walls or where the spillway met exposed rock, workers bent the rebar to match the terrain, ensuring proper anchorage and a seamless structural connection. Several large rebar panels were pre-welded into modules offsite and lowered into position by crane to speed up the installation process. Once the entire reinforcement grid was completed, it formed the structural skeleton that would carry the load, ready for the final step of placing the concrete surface slab. With the rebar grid fully in place, concrete trucks began loading fresh concrete directly from the mixing plant, where the temperature of the mix was tightly controlled by injecting liquid nitrogen to cool it down, preventing the concrete from overheating in California's weather and cracking prematurely. These trucks moved non-stop to the base of the structure, then queued up as they climbed the steep spillway ramp to keep pace with the day's pouring schedule. At the work area, a chute or pump line was extended out to discharge each batch of concrete onto the green epoxy-coated rebar below. Workers used internal vibrators and surface vibrators to remove trapped air, ensuring the concrete filled every gap around the steel and bonded firmly to the RCC foundation. The surface slab typically ranged from 12 to 18 in thick, strong enough to withstand the immense water velocities during spillway releases. Concrete placement continued from early morning until nightfall, because any long pause would create cold joints that weaken the structure. Section by section, each slab was finished seamlessly, forming a robust, high-strength surface for the new spillway. After the fresh concrete was placed over the rebar, workers used long screed bars to pull and spread the mix evenly across the entire surface, making sure there were no low spots or areas lacking material. Moving along the form edges, they constantly adjusted the concrete to reach the exact design elevation. Next, power treels or hand trowels were used to smooth the surface, lightly compact the top layer, and create a uniform texture. This finishing process also helped remove surface air bubbles, forming a dense, smooth, and durable top layer. After finishing the edges and tight corners by hand, the crew moved on to treating the larger surface area using automated rollers to speed up the process and achieve a more uniform finish. At this stage, along with manual placing and leveling, automated rolling machines were brought in and guided along rail systems to flatten the concrete. While it was still fresh, these rollers both vibrated and pressed downward, helping to force out air bubbles and densify the concrete with just a single pass. Thanks to this pour and finish as you go method, the team significantly increased production speed while still maintaining a high-quality surface. Finish. After the concrete layer has dried and hardened sufficiently, after the RCC layer had dried and reached sufficient strength, usually after 1 to 2 days, the construction team began cutting expansion joints across the surface using high-power saws. These joints allow the concrete to expand and contract with temperature changes without cracking, which is especially important for a spillway stretching hundreds of meters. Next, workers installed the subsurface drainage pipes in their designated positions. These pipes allow any water seeping beneath a concrete layer to exit safely instead of building up and creating upward pressure on the spillway surface. Afterward, they filled the water pipes with treated soil and rocks to secure the drainage system and protect it from damage. This system includes 55,000 feet of drainage pipes, and if you stack them vertically, their combined height would stretch over 10 meters. Next, the crew began assembling the sidewall framework using a massive reinforcing steel system. Large green epoxy-coated rebar panels pre-tied on the ground were lifted by heavy cranes and set precisely into place along the edges of the spillway. Workers then connected each panel with wire ties and steel plates, forming a continuous, heavily reinforced wall structure capable of withstanding the extreme hydraulic forces that occur during high-flow releases. Temporary bracing was installed immediately afterward to keep the steel framework stable throughout construction. Once the entire reinforcement system was secured, the sidewalls were ready for the next phase, installing formwork and pouring the concrete that would create the finished spillway walls. Once the rebar framework was securely in place, the crew installed steel formwork around it to shape the spillway walls. Fresh concrete from the mixing plant was pumped up through high-pressure lines, flowing continuously into the space between the formwork panels and encasing the entire steel structure inside. During the pour, workers used internal vibrators to consolidate the concrete, ensuring it filled every void and eliminated trapped air, a critical factor for achieving density and long-term strength. The wall was poured in lifts with each layer checked for proper elevation and vertical alignment using a laser system. When the concrete reached the design height, the form top was closed off and the upper surface was trilled smooth to create a clean, uniform edge. Finally, the wall was left in place for several days to cure before the formwork was removed. Next came an equally important component: the teeth or energy dissipation blocks at the end of the spillway, the point where the water must be redirected and slowed before entering the downstream channel. These structures are built entirely from reinforced concrete and engineered to withstand massive impact forces as water crashes into them at speeds of tens of meters by breaking up and dispersing the flow's energy. These blocks protect the riverbed and the entire spillway structure from erosion. After completing the main spillway, the construction team moved on to reinforcing the emergency spillway, using the same roller compacted concrete RCC method as the main chute, but over a much larger area. Heavy-duty trucks continuously delivered RCC to the base of the site, dumping it in thin layers about 8 to 12 in thick. Bulldozers and vibrating rollers worked together to level and compact each lift, transforming the old ground surface, once just a natural hillside, into a massive erosion-resistant concrete platform. This process was repeated hundreds of times, creating a concrete splash pad roughly the size of 25 football fields, capable of withstanding the sheer force of billions of gallons of water during an emergency overflow. Thanks to this RCC reinforcement, the emergency spillway can now operate safely and avoid the kind of severe slope failure that occurred in 2017, after all components were inspected and certified to meet standards. The operations team conducted a test release to evaluate the performance of the entire system. The first flow of water was released down the spillway at gradually increasing discharge rates, allowing engineers to observe the stability of the concrete surface, sidewalls, and the energy dissipation blocks at the end. Sensor arrays installed along the spillway continuously recorded vibration levels, movement, and water pressure to ensure everything behaved exactly as designed. When the flow reached its maximum test load without any signs of distress or anomalies, the new spillway was officially declared safe and ready for full operation. And with that, the entire repair process was completed by more than 600 workers laboring non-stop for over 200 days, a massive engineering effort running 24/7 to meet California's rainy season deadline. All the information in this video was compiled from multiple technical sources. So if you spot anything that doesn't seem accurate, feel free to leave a comment and let me know. Thank you for watching, and don't forget to subscribe to Quantivox Tech. See you in the next epic engineering story.